Okay, so there's a reaction between zinc and a solution of copper nitrate. So your job is to determine your products as well as balance the equation. And then I want you to give me the conventional, the total ionic, and the net ionic equations.
Yeah, we did this.
Oh wait, we did this one already.
Oh, okay.
Yeah.
Okay, so then we don't have to do this one, right? Move on. Okay, so then let's talk about activity series. So the best thing about single replacement reactions is that there's a pecking order, right? So just kind of like in life, you know, if you're at the bottom of the totem pole, you always get dumped on, right? The same thing happens with metals. So metals have a pecking order. So your group 1 metals, right? They're pretty high on the pecking order. If you actually take a look, your lithium, potassium, and then you have sodium down here. So these guys are the highest on the pecking order. So in terms of activity series. Now let me kind of explain to you how this works. So basically, the way your activity series is, it gives you the order in a single replacement reaction, who can replace whom on this pecking order. Like for instance, they give you the example, zinc. So you see zinc's down here. Oops. Sorry. It's a rough morning.
Your sister didn't bring you Starbucks today?
No, she didn't bring me Starbucks, and I'm just getting my first coffee right now. I've been emailing and emailing. I'm like, okay, I'll go down and start it. And you know, I have no reason. I'm just kind of like, I get caught up in a really interesting email. So, okay, so zinc is right here, and copper is right here. So zinc metal can replace copper in a single replacement reaction, but copper can't replace zinc. Okay? So like earlier, do you guys remember the reaction earlier with the copper and the zinc? So we had zinc, metal, and it was reacting with copper to nitrate. So this reaction will happen, right? And then you'll get copper plus zinc nitrate, or zinc 2 nitrate. Okay, so this reaction is going to happen where the other reaction, if we had copper, metal, you guys aren't going to say, Dr. Henry, you forgot your aqueous and your solid. You're just going to let me get away with that. Because I'm not going to let you get away with it. Okay, so copper reacting with zinc nitrate isn't going to happen. So it's not applicable. It won't happen at all. Okay? Because the pecking order, copper is lower than zinc. So zinc metal can replace the copper in a solution, where copper metal can't replace zinc in a solution. Do you guys get that?
Yeah.
Okay. So the higher you are on the pecking order, the more people you can replace. Like for instance, we have sodium here, right? So sodium metal can replace all of the guys that are beneath him, but he can't replace any of the guys that are above him. Okay? And this also tells you, these guys are going to replace, let's say, the H from liquid, water. So if you put them and you react them with water, they're going to replace the H from the water, right? Steam or an acid. Here they'll do the same thing. So like for instance, if we have Na plus H2O, you're going to get, oops. You're going to get that happening, okay? So it'll actually replace the H that's in water, and so you end up with sodium hydroxide and hydrogen gas. So the same thing will happen with steam, liquid water, and then also if it was an acid reacting with an acid, it'll replace it like HCl. It'll replace that H in HCl, so you'll end up with salt, and then you'll have hydrogen gas. Okay, so here, these guys are going to replace the H2 from steam and just an acid. So they can't do liquid water, they're not as strong, right? And then these guys can only replace it from an acid. So these guys won't react with liquid water or an acid or steam, okay? Do you guys get that?
Yeah.
So you'd expect to see no reaction to occur if you had these metals in with water or an acid or steam. Okay, questions, concerns, Cash? You guys want to give it a shot?
Yes.
Okay, so let's say we had okay, what will we get out of this? Is it going to be a reaction or is it not going to be a reaction?
There will be a reaction?
You said yes or no?
Yes.
Okay, so what are going to be the products? Now you guys can help her out. She ain't doing this all by herself. This is a team effort.
Would the K replace the calcium?
That is correct. So then it would be K. What?
CL.
CL.
KCl.
ACL. AQ.
AQ, that's right. And
Calcium.
okay, is it balanced?
No, because we
No.
don't have 2 chlorides on the product side.
What do I need to do?
Put a 2 in front of the K on the product side.
Okay. Oops. Sorry. Is that what I needed to do? I heard a
Yeah.
little bit of Kayla and a little bit of Matt. I should say, am I clear? Is it coming out clear, or is it getting staticky? Like
It's
going
clear.
in and out. It's clear? Okay, good. Okay, piece of cake? Okay, let's try one more. Okay, are we gonna get a reaction?
Yes.
Are you
No.
I don't know if the iron weaker, so it can replace.
So where's iron located at? Iron is here.
Right.
Yeah.
And
oh, manganese.
So manganese is higher than iron, so it's not going to replace it. So where we saw that the potassium earlier is higher than the calcium, so we can replace it.
Oh.
Okay, you see how that works?
Yeah.
Then you just write Na, not applicable. Or NR, no reaction. Both of those are acceptable. Okay, you want to try one more?
Yes.
Yeah.
Yeah.
Okay, so let's say we have that one, and then let's do and okay. So the first one, we'll call it A. What do you guys think?
Yes.
Okay. So then what will be the products? Assume that you're going to have copper 2 ion.
Is it copper nitrate?
Okay. So if it's copper 2, the ion that it forms, so how many nitrates will I need?
2.
Okay.
Then what is the other product?
Silver.
Okay. What about this guy down here?
Yes, because it's an acid.
That is correct. Okay, so what will be the product?
BSNCl.
And
Plus H2.
yeah, I think 10 is 10 2, but I'm not 100% sure. I have to look that up. So is it balanced?
No.
Put a 2 in front of HCl.
Okay. Okay, what about the last one? Come on, come on.
Aluminum chloride.
So you say aluminum chloride?
Uh-huh.
Do you guys all agree?
I thought you couldn't do that
Ah, why not?
because the AL is lower than the Mg.
That is correct.
Oh, okay.
So, NR. Okay, piece of cake. So these are like one of my favorite types of questions. I love these questions. Hint, hint, hint. Okay, you guys ready? Move on.
Would we be able to use this chart on our exam, or do we need to memorize it?
Yep, it should be in your packet, I believe.
Awesome.
Oh, yeah.
So just remember hierarchy and think about the metal. Think about metal as priority. So the higher you are, you can replace anybody who's below you, right? Kind of like in life. Okay, let's see, let's see, let's see. Okay, so we also have oxidation of common organic compounds. And so the oxidation of those things are basically when you add oxygen to it or combustion reaction, right? So in this case, let's say we have a general compound. This is like a very generic equation. We add oxygen gas to it, and you're always going to end up with carbon dioxide and water. All combustion reactions, that's what you're going to end up with. As long as there's oxygen, you're going to end up with carbon dioxide and water. Okay, So you'll also hear a question will ask you if propane is oxidized, right? So basically you're doing a combustion reaction. You guys get that? Hello? Are you there?
Yes.
Anyone?
So,
Yeah.
Dr. Henry, you're saying that a combustion reaction can also be an redox reaction?
It can be a redox reaction, yes.
Okay.
And then often the oxidation occurs when you're adding the oxygen. So then the oxygen is going to be what's going to be reduced. And then the carbon, the organic compound, is going to be oxidized.
Okay.
Okay. So write the equation for the complete burning of ethane. Now, anytime you hear the word burning, you assume that there's oxygen is going to be present. So how would you do that? Anyone? Where we're going to start? Okay, it's not Monday. You can't use Monday as an excuse. Come on, let's go.
Start with the given.
Okay, what's our given?
It's 2H6.
Okay, so let's go ahead and put that in our equation. So what else is going to be present? What's present in air that we need to breathe?
Oxygen.
Oxygen.
Okay. And all reactions that require combustions or burning is going to have, guess what?
Oxygen.
Okay, now what does oxygen look like?
O2.
O2.
So what are going to be our products? What do we breathe out?
CO2.
Carbon. CO2.
CO2, carbon dioxide. I heard somebody say carbon. I know what you meant. And what is going to be the other product?
Water.
Hydrogen.
That's right, water. Not just hydrogen, water. Okay, so this is the way I think about it, right? So anytime you eat, right, you go, and then you have to take a deep breath. Think about oxygen, right? Think about Thanksgiving. You eat, you're like, you're getting all that carbon in. And then you have to take a deep breath to get that oxygen to help you digest your food. And then you breathe out, right? You breathe out that carbon dioxide. And then a little bit later, you got to go tinkle. And that's going to be your water. So that's how I remember it, right? And if you think about it like that, you will never forget. I breathe in oxygen, I breathe out carbon dioxide, and I have to go pee. Okay? Or pie. Okay? So now we need to just balance our equation. How can we balance our equation?
Write down your elements.
Okay. So I got Cho written down. Come on, at this point, you guys all should be
Okay, so
chiming
you
in.
have 2 carbons, 6 hydrogens, 2 oxygens.
Okay. So we have 2 carbons, 6 hydrogens, and 2 oxygens. Okay.
Okay.
On the other side,
On the other side, 1 carbon.
1,
2
2,
hydrogens.
3.
and 3 oxygen.
okay, is it balanced?
No.
Nope.
No.
So put a 2 in front of CO2.
That'll make it 2.
The C. The carbon.
And then that's what? 2 times 2 plus 1.
4.
So altogether 5.
Yeah.
So is it balanced?
No.
No.
But we have our carbon balance though.
Yes.
What about the hydrogen?
If we add a 3, it'll make it 6 in front of the
Okay.
H.
Okay, so that gives me how many carbons? I mean, oxygens?
18. 9.
It's 2 times 2 is
4.
4 plus
So 7.
7. Is it balanced?
No.
No.
Oh, and it's an odd number.
Yeah.
So what do we need to do?
Change something.
Change something. Well, I'm going to show you a trick. If I use 7/2, 7/2 times 2 is what?
7.
Is it balanced?
Yeah.
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 So now here's the hard question. Can you have a half of a molecule?
No.
No.
So we want to get rid of the half. So if we multiply everything by 2, the whole equation, we get rid of the half. So we end up with oops. Oops. Okay, piece of cake.
Sure.
You want to try another?
Yeah, probably.
I heard, yeah, maybe.
Yes. Yes.
Yeah.
Okay. So let's assume that we have, instead of ethane, we have butane. Oops, what is butane? Oh, actually, that won't work. Butane works 6, 10. Yeah, butane will work. Okay, so instead of, okay, so what do we need to do in that case?
We would write it out again.
Okay. Okay, so I have it written out. So how do I balance it?
Write out our elements again.
Okay.
So we have 4 carbons on the reactant side.
Okay. So we have 4.
And 10 hydrogens, 2 oxygen.
Okay.
We have 1 carbon,
1 carbon,
2
2 hydrogen, 3 oxygen.
3 oxygen.
Okay.
Four in front of the carbon.
Say that again.
Can put a 4 in front of the carbon.
Okay. Okay.
That'd give us 9 oxygens.
Okay. Is it balanced?
No.
We put 5 in front of the H2O.
Okay.
That'll give us 13 oxygen.
Okay. Is it balanced?
No. Also odd.
Okay. So what am I going to do since it's an odd number?
We use that fraction.
Okay. So we'll leave my
13
fraction.
halves.
13 halves.
And then you multiply the whole thing by 2.
Multiply that.
Then I multiply the whole thing by 2.
That's an awesome rule. I spent so much time trying to balance those odd equations.
But it only works when you have like a single source.
Okay.
It gets complicated when there's others. Okay. So we'll get 2, 4, H10. Plus 13 O2 yields 8 CO2. And don't forget to multiply by everything. That's usually the most common mistake that I make.
That makes it easier.
Piece of cake?
Yeah.
Yeah.
Okay. So let's try one more time. Let's say we're reacting it with azide, or sorry, is it peroxide? Or ozone, sorry, ozone. Ozone is O3. So it's going to be a pretty hot reaction. So what are we going to do in this case?
Count your elements.
Okay.
So you've got 4C on the reactant side, 10 hydrogen, 3 oxygen.
Okay. And on the product side, oops.
1 carbon, 2 hydrogen, and 3 oxygen.
Yeah.
Okay, is it balanced?
No.
No.
Okay, so how do we balance it?
Put a 4 in front of CO2.
4 in front of CO2, okay. How many oxygens do we have now?
8.
8. Or 9, sorry.
9, okay. And then
You have 10 hydrogens.
we need to change 10 hydrogens. So what do I need to do to get 10 hydrogens?
So put a 5 in front of
Put a
H2.
5.
H2O.
Okay. So that gives me 10 hydrogens. How many oxygens?
Over 9.
Go to F1.
Oh,
13.
13.
13. Okay. So what do I need to do here?
Oh,
I have 3 and 13.
You would have to do the
13 over 3.
13
right.
over 3. Good job. So then we multiply by what to get rid of the 3?
By
3.
So do you guys see that?
Yes.
Yeah.
Yeah.
Okay, piece of cake.
Yeah.
See, I figured you guys would appreciate that after you suffered a bit with balancing equations.
Definitely.
That would have made things a lot
You could have
easier.
definitely told us earlier, but I mean, it's okay.
No, I just wanted you to suffer. Come on, you got to appreciate the pain. Okay, you guys ready to move on?
Yes.
Okay, so we've talked about double replacement reactions before, but now we need to start thinking about it in terms of precipitation, right? So there's rules to precipitation, but for you guys, I'm gonna let you guys use this table rather than memorizing all of the rules, right? So when we have a double replacement reaction or a double displacement reaction, we're mixing up partners. So what you wanna do is you wanna sit there and look to see whether or not the new partners are going to be able to form a precipitant. Okay, so is A and X going to be a precipitant, or is B and X going to be a precipitant? The way that we would do that is by looking on our table. And it's so funny. Yesterday, Andy asked me this last night. So how do I know what's a precipitant, right? So let's say we had we have ammonium ammonium carbonate. Carbonate. Reacting with barium chlorate. Okay. Both of these are aqueous solutions, or we'll say solutions. This is my abbreviation for solution. So I want you to write a balanced equation and predict the products. You guys got that? Here, and I'll give you another one, and then I'll put you in groups. How about that? And everybody has their table, right? Okay. So, you guys ready? Let's save it so I don't lose it. Okay, you guys ready? Okay. See those skills?
Who's gonna write?
One.
I'll do the ammonium carbonate one.
Wait, what group am I in?
Group 1.
Okay. Well, who's gonna write group 1? Anybody?
What?
I'll do it.
You're awesome.
In the group with Selena and Matt and Deandra.
It's group 3.
I know. Which one which one of us wants to go up there, you guys? Do you want me to try it?
I mean, I'll do it, but if you guys help me.
Okay, how about do you want me to write what I got, and then if you think that it's incorrect, let me know.
Okay.
You guys didn't talk about this when you're in your groups?
We didn't get too far.
And what exactly we needed to do. So we got one problem down, but it's okay because we figured it out.
Okay.
Judy, I think you were in group 1.
Okay, I'll write the other one. Since there's 2 group 1s, I'll do.
That's funny.
Juan, you said you're doing the ammonium carbonate?
Yeah.
Okay, I'll do the strontium one. Ah, hell, you gave me that one. That one out of
Okay, I'll I'll do the cobalt nitrate. I don't know who's gonna do the other one, but for group 2, I'll do that cobalt nitrate solution.
Okay, Matt, I'm the group 3 one.
No, you can stay on here.
See the bottom of the screen. What are the ones that group 2 get?
Group 2 got
Cobalt nitrate and nickel metal reacts with silver nitrate.
There's another little Miata in the neighborhood.
Oh, you're gonna start a Miata club? Ooh, yeah.
Did you say a Miata club?
Girls' place because they did the shrubs.
Yeah, my guy has a toy car Miata that he's vrooming around everywhere. And then what's funny is that he broke it in Avenal. So I had to go and rescue him in Avenal. Oh my goodness. That is why I was not in lecture in the morning. I was there, but I wasn't there. So
Okay.
It's your fault. Yes, your fault.
Oh my gosh, how do I change the color?
Oh, shoot.
Why is it not drawing? Oh, it is. It's just super light. You guys know how to change the color of the...
You hit format?
There's not one spot. Wow.
Under annotate, there should be a format, and then you'll have all the colors available.
Damn it.
Let me exit out of that. There we go. Thank you. Oh gosh, terrible.
Oh my gosh, I'm so tired. It's like so much harder on iPad. I need a stylus.
I've been on hold for 2 hours and 10 minutes.
Well, then why don't you just go and get the dang range yourself?
They approved it, so they had to send it.
Dang, 2 hours and 10 minutes, that's a long time.
I know.
2 hours.
I don't know if that was right, Dr. Henry, but
Matt, Selena, Deandra, what do you guys think? Anna.
I'm kind of down a rabbit hole right now.
What do you mean by that?
Face right now, trying to see.
A rabbit hole, like Alice in Wonderland.
I'm trying to read him.
Couldn't read who?
You. I'm trying to read your reaction.
There's like 50 things up there, so how can you tell which one I'm reacting to?
I know.
I'm just going through my sheets here. Am I missing something? I think I'm missing something.
Sorry.
would sodium hydroxide, wouldn't that be 2 NaOH?
I think a hydroxide is just a negative charge. And then Na is a plus sign, right?
Wait, Dr. Henry.
Yes.
In most chemical, sorry, in most chemical equations, like how would you know when something is like a solid, liquid, or gas?
Well, you know, well, so one thing you know if it's a solid if it's a precipitant, right? So if you look on it, if you look on that table, anything that's in that pink on your table, or pink or orange pink or whatever color that is, you see my table? So all of that stuff that's in pinkish, orangish color, so those are all going to form solids. Anything in the green is going to be aqueous. And then, so you're going to either have aqueous and then liquids. It'll usually tell you it's liquids. Water is a liquid. So pure liquids is the only thing that we will put in the terms of liquid. So if you have water dissolving something, that's not a pure liquid, so that's going to be aqueous, right? So anytime you have an ionic compound, that's going to be aqueous. And then solid, if it's a precipitant, it's going to be a solid. If it's a metal, it's going to be a solid, right? And you know your noble gases, they're all going to be gases. You know your diatomic, most of your diatomics are gases, although iodine could actually be it could be a solid or a gas.
Okay.
Does that help?
Yeah, so like nickel hydroxide, if we were to look at the solubility, it's nearly insoluble, so you would write solid?
That is correct.
Oh shoot, I didn't put my stuff on there. Oops. Fail.
It looked like a G, so I'm changing it.
Yeah, if it's in pink, if it's nearly insoluble, basically it means that the majority of it is insoluble, but you only have a little bit that's still soluble. If it's slightly soluble, meaning again, the majority of it is soluble, the majority of it is a precipitant, only a little bit of it is soluble. Soluble meaning you're able to dissolve it in water.
Okay. Thank you.
You're welcome. That's actually a good question.
I'm sorry, Matt, were you saying that there was something up with this one? Did I mess up somewhere?
Well, this is kind of what I was thinking, like your sodium goes with your hydroxide, which would be your aqueous solution. And the nickel nitrate, you would need 3 nitrates to balance out your nickel.
But I think in the question, nickel has he gave us the 2 charge.
That is correct.
Okay.
Nickel 2.
So that's a 2 plus and the nitrate.
Now you guys want to balance your equations too,
so
right?
We need 2 of these here then.
You guys are very parentheses happy.
Ooh.
Okay, so should I start with the first one and work my way down?
Skip group 3 for a second.
Okay.
Yeah. It's probably all wrong, but.
Okay. So let's start off with, I'm going to bring out my red pen. Red pen. Red pen.
Oh no, it's never good.
Okay, so let's see. So that's looking good right there. Okay, this part here.
Oh, that's black.
Make sure. Yep. So that's, oops, although that's a black pen, sorry. Let me fix that. Red pen. Okay, and then that's incorrect as well. You don't need it. So that's beautiful. And yep, that's good. So look at iron 2 chloride. Is it soluble on your table or is it insoluble? Or nearly insoluble? Soluble. So soluble means that it will be aqueous. You can dissolve it in water.
Okay, let me see if we can.
Okay, so I'll skip over this one right here. We'll come back to it. Draw arrow. Okay.
I can't delete your stuff.
What was that?
I can't delete your stuff, your annotation.
There you go. Okay. Okay, Judy.
Yes.
Okay, so this is sort of right?
Mm-hmm.
But, so yes, so technically your answer is going to be correct. So this is actually going to be a precipitate. And then you're going to get a gas and it's all going to be in kind of a still liquid solution. So your answer is correct.
What could fix it though?
It's correct. You just have to remove your question mark.
Oh, okay. Got it. Thank you. That was all Juan, by the way. Woo!
Good job. Yeah, because strontium hydroxide is actually, it'll form a precipitant. And so it'll actually precipitate out.
Okay.
Okay. Let's see. Nickel. Okay, that looks good. Looks good. Let's see, make sure we're right in terms of the numbers. 2. Okay, again, you just don't need these guys here. But otherwise, it's correct. You just don't need your parentheses for this guy.
Would it be all the time that we don't need the parentheses, or in what situations do we need the parentheses?
The only time that you need a parentheses is if you're putting a number next to what's in your parentheses. Is there a number next to this guy?
No.
Yep. And then you don't need a parentheses if, like, in this case, you have a number next to it, but it's understood that it's just next to this one element, right? So you don't need to put a parentheses there. You understand? So it's understood that it's just this guy, so you won't need one there.
Okay.
I'm gonna. Sorry. Those little things, you know. Okay. So, let's see, 1. You have to write so damn small, Juan. I have to get up real close. You make me feel old. That is lovely. Good job. And no excess parentheses. Good job. Good job. Okay. I can't even read yours. It's just so many stuff, so many things going on there.
Somebody also typed on it, so I don't know how to move it.
Oh, okay. Which one are we moving?
Yeah, that's where I had it, and I wrote some stuff on it.
Oh, I see. So like this.
Yeah.
Okay, so let me move the stuff that they typed and then I'll move that back.
And I'm trying to fill in the coefficients.
Okay, so for the coefficients, so I wrote down the elements that I was given.
Mm-hmm.
And so I had to balance, I had to put a 2. So on the product side, the NiOH, and we had in parentheses 2. That tells us that there was the 2 subscript applies to the OH. So and on the reactant side, it was just NaOH. So I added a 2 in front of NaOH so that I would have 2OH. And then I'm sorry.
I'm a little lost. Do you want to annotate it?
Okay.
Yeah, I'm trying to delete that little.
Remember the 8?
But it deletes the whole thing.
It's okay.
Yeah.
Sorry.
Is that good?
Thank you.
Yes. So what I did. Now I don't know if I'm correct, but I have so many things written down. So there's a 2 over here. So I added. And then to balance out the Na over here.
Thanks, Deandra.
You're welcome. I mean, I don't know if that's correct. That's what I got.
Okay, so your numbers, your coefficients are correct. Okay, again, I'll mark off what's wrong. And what I would
And then
dock you
for the elements, I just put like NaOH. I didn't put the OH in parentheses. I kind of just combined it all into one.
That's correct. So. That one is correct. And let's see. Oops. Sorry. And what about over here? You also would need this guy or this guy.
Right. But you would need the, for NiOH, you would need to add that 2 behind OH.
That's correct. Okay. There you go. Piece of cake.
Good job, team.
Okay, questions, concerns, Cash?
When you guys are saying about the parentheses,
Yep.
that it's incorrect with the parentheses, why is that?
Because here, the OH, although it represents an ion, you never want to put the parentheses unless you have a number following that. So is there a number following the OH?
No. Okay.
Okay. So like here, there's a number following the nitrate. So you want to put, because you need 2 of those. So here you don't put anything following it, right? It's just the nitrate, no parentheses.
Okay.
Okay.
Thank you.
No problem. Okay. So kind of clear? Everybody got it down?
1 second.
Okay, good job, good job. So you guys understand how to use the table, right? Now it doesn't want to show. Okay, the pink and the green, remember, pink precipitate, the green mean aqueous or soluble. Okay, so this is what I make the 1A memorize, this table here, right? So they have to know what compounds are soluble and which compounds are insoluble. So you notice that sodium, potassium, they're pretty much always soluble. Group 1 metals are going to be pretty much all soluble all the time. Okay, and then these are your exceptions. Okay, so acetates isn't going to be soluble with aluminum. So aluminum acetate isn't going to be soluble. Silver acetate isn't going to be soluble. It's going to be insoluble. Silver nitrite is insoluble. So these tell you these guys they're insoluble with that. So again, you guys just have to worry about the table, not so much about this. My 1A class has to worry about this. So, right, Jessica? Did she dump me?
No, I'm here.
Okay. So you guys already done a practice problem, so you can save this one for later when you're feeling frisky. Okay, so we also have the case of acid-base reactions, right? And you guys are already familiar with that, right? Acid-base reactions. So the one thing about acid-base reactions, we have what they're called neutralization reactions. So basically, you're always going to end up with a salt and water. And I think we talked about this last time too, right? In chapter 8. Okay.
So.
Dr. Henry, so a precipitate and an insoluble, is that the same thing?
Yep. A precipitate means insoluble. So basically they're coming together. They can't be redissolved, right? They don't dissolve in water. Okay. So a precipitate or insoluble are comparable. They're the same. Okay. So you guys are very familiar with writing conventional ionic equations and net ionic equations. So can you guys do this for hydrochloric acid and sodium hydroxide? Any volunteers? I'm going to sit here and drink my coffee and look pretty. Or dude, somebody needs to be voluntold.
Okay, I'll do it.
Okay.
Okay. Correct me if I'm wrong, y'all. Write the conventional for the reaction between solutions of hydrochloric acid and sodium hydroxide. So hydrochloric acid is HCl, right?
Yeah, and sodium hydroxide is NaOH.
Gosh, hold on. It's gonna be aqueous, and then NaOH, and that's aqueous as well. And then it's gonna make NaCl, sodium chloride. Sodium chloride. Sodium is a 1 plus -1. And then that's gonna be on our table here, sodium and chloride. It's table salt, girl. It's just freaking solid. The hell gotta look at a table for?
Is it gonna be a solid?
I don't know. Is it?
You're putting it in water, right?
Oh, it's aqueous.
It's an aqueous, yeah.
It's, yes. Aqueous. And then it's gonna make OHOH. H2O, right? Anybody help me?
Yeah.
Liquid, right?
Yeah,
Liquid.
that's right.
Okay,
Yeah.
then let me see if it's balanced. I have 2 H's here. 1 oxygen, 1 Na, 1 Cl. I think it's balanced.
It is balanced.
Okay, so that is my conventional. And then my ionic is going to be H plus. H plus, would that be solid? Wait, I don't think we put the states when we're doing ionic, right? We just put the charges because it's, right?
Yeah, I think so.
Okay.
I think you do put them.
Yeah, you do. I'm looking back from the previous examples and you do.
So that one's aqueous. This one's aqueous. This one's aqueous. And then plus OH, Na plus 1, OH negative, aqueous. And that's going to be 1 Na plus aqueous plus Cl negative aqueous plus
H2O.
Oops. Plus
H2O.
2H. I think it would be 2H plus.
I think it will just be the H2O, the same, yeah, H2O, and then liquid.
H2O liquid?
Yeah.
You want to break it down like everything else?
I think because if it's a liquid, gas, or solid, it remains the same.
Okay. Okie dokie, which one looks the same? Oh wait, this is our ionic, and then our net ionic is we're gonna take away the spectators. So which ones are the same? I think that the sodium's the same.
And the chlorine?
And the chlorine is the same. So I just have the H plus. I don't keep the charge up here, do I? Or would it just be like this?
I think you do keep the charge.
Yeah, I think you do keep the charge.
Okie dokie.
And
so
then
I'll just write the ones that are not simple.
And then H2O liquid.
Like that?
Yes.
Yep.
Good job.
Okie dokie.
That's it. Piece of cake?
Piece of cake.
Okay, so that is good. Good job, guys.
Thank you, everybody.
Okay, so let's go. Keep going.
I'm trying to clear it. Oh, there we go.
Okay, so sometimes we get things that are unstable, and so they end up with other products. Here's an example of one of those situations. Oops. Okay, so here's an example of 3 cases where we have unstable products, right? So we have the carbonate or carbonic acid. So basically, carbonic acid, initially it forms that acid, but then it breaks down to carbon dioxide and water. Okay, here, sulfuric. So if you have these ions, what will happen is that they'll form a temporary sulfurous acid, which will be broken down to sulfur dioxide and water. And then if we have these 2 ions that end up coming together, they're going to form ammonium hydroxide, and then that's going to be stable for just a minute, and then you're going to end up with ammonia and water. Okay, so these are ones that you want to kind of keep in mind. So if you have these ions that are forming, then what's going to happen, they're going to form that acid, and then they're going to break down further. So they're going to be unstable products. You guys get that? So if you have 2 things, and these are the things, these are your 2 ionic compounds that are left over, right? Then you know that this is what's going to happen. It's going to break down to carbon dioxide and water, sulfur dioxide and water, and then ammonia and water. Okay, and that's just for these guys. Okay, and sometimes we end up with cases where we have no ionic products, right? Or your net ionic, you have no product left over. So then those reactions won't exist. You just have all your ions in solution. So like for instance, let's do nitrates. Let's do something with the nitrate. Do sodium nitrate and potassium chloride. Okay, so in this case, we have, what is the chemical formula for sodium nitrate?
NaNO3.
Solid, liquid, gas, or aqueous?
Aqueous.
Aqueous.
And then plus potassium chloride.
HCl.
ACL.
Solid, liquid, gas, or aqueous?
Solid.
Potassium chloride solution.
Aqueous.
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 So what would normally, for the conventional reaction, what's going to happen?
The
Sodium chloride.
Solid, liquid, gas, or aqueous?
Would that be your?
aqueous.
Yeah.
And?
Potassium
nitrate.
Solid, liquid, gas, or aqueous?
Aqueous.
Aqueous.
So this should be a dead giveaway, the fact that you have everything in aqueous. So when you do your total ionic equation, what are you going to end up with?
Total was the one where we took away the spectators, right?
No. Total.
No.
Total is where we have everything broken down into ions.
Oh, gotcha. Na plus plus the NO3 negative 1 aqueous plus the potassium plus 1 aqueous plus the Cl minus 1 aqueous. I think they're all gonna be crossed out.
That's right, and that's the point. So when you end up with something that has aqueous and aqueous and aqueous and aqueous, right, on both sides, you're pretty much guaranteed that they're going to cross out. You don't have a solid or you don't have a liquid being formed, right? So you're going to end up with everything just ending up in solution as ions. And so you won't have a reaction. So so this guy would not react. But you just say NR. So that's why it's important that you put your states on there.
Mm-hmm.
And you make sure that you have the right states. Okay? Piece of cake?
Mm-hmm.
Oops. Just one more time. There you go. Okay. So in this case, I'll give you an example of the unstable states. So if we write down the conventional total ionic and net ionic equation for the reactions between sodium carbonate and hydrochloric acid. So what are we going to get? What does sodium carbonate look like?
NaCO3.
Yeah, so they went, they
Am I missing anything?
Na2.
Na2. There we go. And it reacts with hydrochloric acid. What does hydrochloric acid look like?
HCl.
What it looks like.
not yet.
Okay. And it's going to make?
So you're going to combine, so it's going to be NaCl.
Yeah.
And?
Oh my God. So I'm going on 3 hours.
CO.
Up on that phone and
CO. 3.
yes.
Okay. So we know that this guy, once it forms, it's going to be a temporary formation. And you're going to end up making
H2O.
Okay. So, and that's just this part here. So your overall equation is going to be or conventional equation. Okay, so what will be my total ionic equation?
Na.
Na plus, CO3 negative,
Oops, I forgot my 2 here. Sorry.
aqueous,
Oh, is our equation balanced? We have to do that up here. This guy here. Is it
You
balanced?
need a 2 coefficient in front of the HCl on the reactant side.
Okay, that's it.
Mm-hmm. No. Then you need a 2. There's 2, and you need a 2 in front of the any on the product side. And I think you're good.
Okay. So then we have 2. There you go. Plus. Okay. You guys are sent H.
plus, and Cl negative, aqueous.
2 Cl. Since
Yeah.
there's 2 of them. Aqueous.
So 2 Na plus, aqueous, plus Cl negative, aqueous.
Okay.
Plus H2 positive, or H2O.
Isn't it supposed to be 2 Cl negative?
Oops, sorry. Thank you. He did say 2, and I just forgot it. Okay.
See?
Just C?
I don't know what C would be.
Is that C negative?
You tell me. It's CO2G. Is that going to be C negative?
You leave it alone.
We leave it alone, so we leave it as CO2, right? Because it's a gas. So gas, liquids, or solids, we leave alone. Okay, so who are our spectators?
To the sodiums,
Sodiums.
the chloride,
The chloride.
and that's it.
Okay, so our total ionic equation is going to be
CO3 to negative.
Okay, piece of cake. So that's an example of where you have unstable products, right? That breaks down even further. Okay, so you remember the three cases. So if you end up with a sulfurous acid, if you end up with carbonic acid, or if you end up with, what was the other one? Sulfuric, carbonic, and there's one more. Oh, ammonium hydroxide. Okay. Questions, concerns, Cash? Can I move forward?
Hang on 1 second.
Okay.
Okay.
Okay, so we've already, so when we have a case where we have something that isn't dissolvable, right? So we have a solid and a solid. And I think we kind of talked about this already. So this would be our conventional equation. So then our total ionic equation when we separate everything. So are there spectators?
Yes.
3 Cl aqueous.
So then our net ionic equation is going to be just that. Piece of cake?
Mm-hmm.
Okay. Can I move forward or should I slow down a little bit? Okay, that means I'm moving forward. Okay, so we've already done this one. We just did it earlier, the one with the sodium chloride and the potassium nitrate. So where we have everything's in that ion. And so we won't get a reaction at all. So we put NR for no reaction. Okay? Questions, concerns, cash, money. Okay, this is just a summary of everything that we've talked about. How you feeling? Good? Bad? Ugly?
Okay.
Okay. Okay. So I'm going to stop here. So to give you time.